Rather than think mathematically, let's start to think a little bit more conceptually about what's going on with a reaction rate. So you see here, this section includes the word temperature. And what they say is that you have an increased rate for most reactions, and again, it's based on observation. If we were in the lecture hall, I would have some light sticks. I'd put one of them in hot water, I'd put one of them in cold water. You would see in the hot water that it is brighter, and that's because the rate is faster at a higher temperature. I would also have Alka-Seltzer in a vessel where a balloon would measure the CO2 coming off. We would see different sizes of the balloons at different temperatures, cold room temperature and hot water, with hot water being the biggest. We had one more demo. I would be doing luminol. I would be reacting with peroxide, and what you would see is light energy. It's really a good demo, okay? So if we look at the rate law, this is a generic rate law, and if you look at that, where could temperature play a role? Well, temperature cannot affect the concentration. So that means the rate constant K has to change with temperature. Very important concept, all right? So when people tried to explain what's going on, their first model, number one, was the collision model. And they said molecules must collide to react. So if I take hydrogen and iodine and react them together, I can say there are 10 to the 10th collisions per second. Okay, that's a huge number. But when I'm at room temperature, the reaction is very slow. Only 1 in 10 to the 13th collisions is successful. Only a small fraction of collisions will lead to reaction. Well, why? As you increase the concentration of reactant, of course, the number of collisions will definitely increase. You do expect the rate is also going to increase, but molecules have to have the proper orientation. So if I say A2 plus B2 is going to form 2AB, what's really happening? Well, those are the original bonds of A and B, and as reaction proceeds, what we see is a breaking of the A bond and the B bond, and eventually the lining up to form the new molecule. But again, has to have the proper orientation for that to occur. So, if you're planning to take the MCAT, PCAT, or any other professional exam, there's often a section that has a number of paragraphs, and this comes from one of the sections where they talk a little bit more in depth. If you talk about the rate of a reaction, I'm just going to have you take a look at this, the PFZ, number of collisions per volume per time. What is P? Well, that's the proper orientation. What's the probability of that's occurring? What about the F? That's the collisions that have the minimum energy needed for reaction. And what is the Z? Well, it's how frequently do those collisions occur. Normally within this paragraph, they'll make a statement. With a 10% temperature rise, what do you predict? Well, it may be buried there, but there's only a 2% increase in the frequency of collision, but there's a 200% increase in the fraction of collisions with minimal energy. I'll go into that 10. All of that is good, but there were some shortcomings. Maybe you wondered, why is there that minimum energy? Where did that really come from? And I'll be honest, you have to have a very simple system for that to occur. Detail right here. When we were back in chapter 10, we learned the average kinetic energy of a collection of molecules was proportional to the absolute temperature. We drew pictures that look like this. If blue right now was the lower temperature, if I increase the temperature, I would shift that distribution. Well, when I shift that distribution, I have more molecules that have sufficient energy to react. So I'm trying to tie it back into something from... So what is our second model? This is number 2, and it's currently accepted probably in a much more modified form. Arrhenius, the same person that brought us ions in solution, he said that molecules must have that minimum energy to react. And where can the energy come from? Well, it's kinetic energy. and it comes from the colliding molecules. And what happens is bonds can be stretched, bonds can be bent, and bonds can then break. We'll go into more detail in the thermodynamics chapter. But what you do with the transition state model is you do something called monitor the progress of a reaction. Like, what does that mean in English? The picture below shows us. Here we have the reactant, here we have the product, and here we have what is called the transition state. And what we put is potential energy on the y-axis. We put what we call the reaction coordinate. I like to call it the progress of the reaction. And let's say, why did I say that? Well, here I have my reactants, and here I have my products. We know they had to progress from one side to the other. Notice they have a hill to climb, and that hill takes us to what is called the activated complex that can form. What can happen? Well, to be honest, they can go back to reactants, or they can go on to form product. And that's the artist's rendition that's sitting in your, all right, and I'm gonna just go back to this for a second, because this progress of a reaction, that's what we'd like you to see as brand new. How do reactants go on to form products? How there is an EA, an activation energy, in order to get to what is called the transition state or the activated complex. Textbook. So if you say, like, what in the world is an activated complex? Well, it's a very unstable grouping of atoms. When I drew my A, B, B, that's really what I was referring to. They can break up to form products, or they can return to go back to reactants. Notice its definition. It says it's found at the top of the energy barrier. Again, terms you've never seen. But that activated complex, we call it an energy barrier. Think about someone putting in playing golf. They're going to try to hit their ball over the ridge and make it go over the hole. But maybe if you've seen enough golf, you've seen the ball can roll in many, many different directions, just like what could happen in a molecule. So people interchange these terms. They interchange transition state with activated complex. The other thing I need to point out is a brand new term called activation energy. And on this picture, it is the line that I'm drawing with the blue arrow, and it's labeled EA. It is, under this model, the minimum energy required in order to have a chemical reaction. Now, let's be honest. It's really going to vary from reaction to reaction. And sometimes people will have you analyze an EA. You will take whatever energy it is of the activated complex and work with the potential energy of the reactants. For many of you brand new, we don't go into much depth. That is about it. We're trying to introduce you to the concepts and what is the picture.